Our Milky Way, a spiral galaxy, is a cosmic city where stars are born, and our sun fuses 600 million tons of hydrogen into helium every second, sustaining life on Earth. Supermassive black holes, millions to billions of times our sun's mass, shape this landscape. Our journey begins in the solar system, venturing into the unknown where black holes, dark matter, and reality's edges await. The Voyager 1 spacecraft, launched in 1977 and now the farthest human-made object, carries a golden record, a testament to our desire to connect with the cosmos. Somewhere out there, between the stars, something is whispering, and we've only just started listening. If this mystery pulls you in, if it makes you feel that quiet chill of curiosity, hit like, subscribe, and drop a comment telling me where you're tuning in from. And if you want to help others hear this signal too, share this video on X, Facebook, Reddit, or even in your private chats. You're not just watching, you're part of the signal. Thank you for being here. In Sagittarius, astronomers discovered Sagittarius A, a star orbiting an invisible point, revealing a supermassive black hole at our galaxy's core. Its gravity warps space-time, yet order prevails. Planets orbit stars, moons circle planets, and galaxies trace the cosmic web. Observation. Since its 1990 launch, the Hubble Space Telescope has captured over 1.3 million images, revealing the universe's intricate beauty. Its deep field image, a snapshot of seemingly empty space, unveiled thousands of galaxies, each a universe unto itself. Interpretation. Each astronomical discovery deepens our understanding of nature's laws. The 2015 detection of gravitational waves, ripples in space-time from colliding black holes, confirmed Einstein's predictions and offered glimpses into the universe's most violent events. Speculation. Could our universe be one of many? The multiverse theory suggests an infinite sea of universes, each with unique physics. Even within our cosmos, mysteries persist. The nature of dark matter, the fate of black holes, and the possibility of extraterrestrial life. These questions drive us to explore, innovate, and dream. Part 1. The Cosmic Symphony. This is not mere poetry. It is the reality of the cosmos, a realm of sound and fury, of whispers and echoes that tell the story of creation itself. Observation. The cosmos is not the quiet void it seems. While the human ear cannot perceive its symphony, radio telescopes pick up whispers from pulsars, the cosmic heartbeats that have pulsed for billions of years. These rhythmic signals are more than just sound waves. They are the echoes of ancient stars, the stories of matter and energy woven into the fabric of space-time. Consider the first pulsar ever discovered, CP 1919, detected in 1967 by Jocelyn Bell Burnell and Anthony Hewish. Its signal, a steady pulse every 1.337 seconds, was so precise that it was initially dubbed LGM-1, Little Green Men, as a playful nod to the possibility of extraterrestrial intelligence. Pulsars are not alone in their cosmic song. Quasars, the brightest objects in the universe, emit radio waves that travel billions of light years to reach us. These distant beacons, powered by supermassive black holes, sing in frequencies that span the electromagnetic spectrum, from radio waves to X-rays. Their light, redshifted by the expansion of the universe, reveals the cosmic symphony's unending crescendo. Meanwhile, the cosmic microwave background, the faint afterglow of the Big Bang, hums at a frequency of about 160.2 gigahertz, a relic of the universe's infancy. Interpretation: pulsars, rapidly spinning neutron stars, emit radio waves with astonishing regularity, like the ticking of a cosmic clock. These signals, some of which rotate hundreds of times per second, are a testament to the precision of the universe's mechanics. They tell us that even in the chaos of space, there is order, a harmony that has persisted since the dawn of time. The Crab pulsar, for example, rotates 30 times per second, its pulses so consistent that astronomers use it to test the accuracy of their instruments. Yet pulsars are not the only keepers of time in the cosmos. Black holes, those enigmatic giants of space-time, also contribute to the symphony. As matter spirals into their event horizons, it emits X-rays in a rhythmic pattern, a death knell that resonates through the cosmos. These signals, known as quasi-periodic oscillations, provide insight into the extreme gravitational forces at play in these regions. Speculation. Could these signals be more than just natural phenomena? Some scientists have playfully suggested that the regularity of pulsar signals could be mistaken for artificial transmissions, a cosmic hello from an advanced civilization. While this remains pure speculation, it underscores the profound mystery of these celestial objects. They are the universe's metronome, keeping time in the vast, silent dance of the stars. The search for extraterrestrial intelligence, SETI, has long been captivated by the regularity of pulsar signals. In 1974, astronomers using the Arecibo radio telescope in Puerto Rico detected a signal so unusual that it became known as the WOW signal. Lasting just 72 seconds, it was a burst of radio waves at a frequency of 1420 megahertz, the same frequency emitted by hydrogen, the most abundant element in the universe. Despite decades of searching, the signal has never been detected again, leaving its origin a mystery. Known, pulsars emit radio waves with remarkable regularity, making them ideal cosmic clocks. The study of pulsars has led to breakthroughs in astrophysics, including the confirmation of gravitational waves predicted by Einstein's theory of general relativity. Unknown. The exact nature of the processes within neutron stars, including the possibility of exotic states of matter like quark plasma, remains theoretical. Neutron stars are among the densest objects in the universe, with a single teaspoon of their material weighing as much as a mountain on Earth. Understanding their interior structure could revolutionize our knowledge of matter under extreme conditions. To be continued. Part 2. The Echo of Creation. What if the universe still remembers its own birth? This question is more than poetic. It speaks to the enduring legacy of the Big Bang, an event that still echoes through the cosmos. The cosmic microwave background, CMB radiation, the oldest observable light, serves as a living fossil of this primordial moment, a faint afterglow whispering secrets of the universe's infancy. This radiation, invisible to the naked eye, bathes the entire cosmos, a constant reminder of a time when the universe was a seething cauldron of energy and potential. Observation. The CMB radiation, uniformly distributed across the sky, is a relic of the universe's earliest days. Discovered accidentally in 1965 by engineers Arno Penzias and Robert Wilson, this microwave radiation was initially mysterious. Working at Bell Labs in Holmdel, New Jersey, they detected a persistent background noise in their experiments, which was later identified as the CMB, a faint, uniform glow permeating the universe. With a temperature of approximately 2.725 Kelvin, this discovery earned them the Nobel Prize in Physics in 1978. The CMB's uniformity is striking, but it is not perfectly smooth. Tiny temperature fluctuations on the order of 1 part in 100,000 were first detected by the COBE satellite in 1992 and are the seeds from which all cosmic structures formed. These fluctuations, though minuscule, are the ancestors of galaxies, stars and planets, their faint imprints etched into the cosmos like ripples on a pond. Interpretation. The CMB is a snapshot of the universe at just 380,000 years old. At this stage, the universe was a hot, dense plasma of protons, electrons and photons, too dense for light to travel freely. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms during an event called recombination. This allowed light to decouple from matter and stream freely through the cosmos. This first light has been traveling ever since, stretching into the microwave range as the universe expanded. The CMB's uniformity reflects the early universe's consistency, while its fluctuations hint at the structures that would later emerge, galaxies clustering like cities on a vast cosmic landscape, each a testament to the subtle variations in the primordial glow. Speculation. The CMB's uniformity poses the horizon problem. How could distant regions of the early universe reach the same temperature? Cosmic inflation proposes that the universe underwent a brief but dramatic period of exponential expansion immediately after the Big Bang. This rapid expansion would have smoothed out initial irregularities, ensuring a uniform temperature distribution. Inflation also explains the universe's remarkable flatness and the absence of magnetic monopoles. However, it remains a hypothesis, and scientists are searching for evidence, such as gravitational waves, to support it. These gravitational waves, if detected, would be like the faint echo of the universe's first breath, a whisper of its explosive beginning. Observation. The CMB is a dynamic source of information about the universe's evolution. Satellites like WMAP 2001 and the Planck Observatory 2009 have mapped the CMB with unprecedented precision. These maps reveal slight temperature variations, subtle polarization patterns, and faint distortions caused by distant galaxies. Planck's detailed map shows fluctuations as small as 1/1,000,000th of a degree, offering insights into the early universe's density, composition, and the nature of dark matter and dark energy. The CMB also reveals the universe's geometry, confirming its remarkable flatness and supporting cosmic inflation. Each ripple in the CMB is a story of the universe's growth, a record of its expansion and the forces that shaped it. Interpretation. The CMB's fluctuations are imprints of quantum processes during inflation. Tiny quantum fluctuations in space-time were stretched to cosmic scales during the universe's rapid expansion, eventually forming the large-scale structures we observe today. These fluctuations are a fossil record of the universe's earliest moments and a snapshot of the quantum processes that shaped its evolution. The subtle polarization of the CMB provides clues about gravitational waves, which, if detected, would offer direct evidence of the universe's explosive growth. This polarization, known as B-mode polarization, could be the smoking gun that confirms the theory of inflation, a subtle twist in the fabric of the cosmos. Speculation. The CMB may hold the key to understanding dark matter and dark energy. Dark matter, making up approximately 27% of the universe, interacts with ordinary matter only through gravity, but its gravitational influence leaves an imprint on the CMB. By analyzing fluctuations, scientists can infer the presence and properties of dark matter. Similarly, dark energy, accounting for about 68% of the universe, leaves subtle signatures in the CMB. Measuring these signatures could shed light on dark energy's nature and its role in shaping the universe's fate. The CMB is more than a relic. It is a living document of the universe's evolution, a testament to its origins and a guide to its future. Like a cosmic Rosetta Stone, it offers clues to the fundamental mysteries of existence, the unseen forces that govern the universe and the echoes of its creation. To be continued. Part 3. The Dark Architects. What if the universe is held together by forces we cannot see? Imagine a vast, unseen framework that gives structure to the cosmos, a scaffold that keeps galaxies from tearing themselves apart. This is the realm of dark matter and dark energy, the cosmos's invisible architects, quietly dictating the fate of the universe on scales so grand they defy human comprehension. Observation. Dark matter and dark energy are the cosmos's invisible architects, shaping the large-scale structure of the universe. Dark matter, which does not emit or absorb light, is detected through its gravitational influence on visible matter. It was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too fast to be explained by the visible mass alone. Decades later, Vera Rubin's groundbreaking work on galactic rotation curves confirmed that something unseen was exerting a gravitational pull, keeping stars in their orbits. Dark energy, on the other hand, is a mysterious force accelerating the universe's expansion. Its existence was inferred from the observation of distant supernovae in the late 1990s, which appeared dimmer than expected, suggesting they were farther away than predicted by a universe expanding at a constant rate. Interpretation. Dark matter is the scaffolding that holds galaxies together. Without it, the visible matter in galaxies, stars, gas and dust, would fly apart under their own rotational velocities. In the Milky Way, for example, stars at the galaxy's edge orbit at roughly the same speed as those near the center, defying the laws of gravity that dictate slower speeds at greater distances. This can only be explained by the presence of a massive, unseen halo of dark matter enveloping the galaxy. Dark energy, meanwhile, is the cosmic repulsive force that counteracts gravity on the largest scales, causing the universe to expand at an accelerating rate. This expansion is not uniform. It stretches space itself, pulling galaxies apart from one another, like dots on an inflating balloon. Speculation. What if dark matter and dark energy are not separate phenomena, but manifestations of a single unified field? Some theories propose that dark matter particles could interact with dark energy, creating a dynamic interplay that shapes the cosmos. For instance, the chameleon theory suggests that dark energy strength varies depending on the density of its surroundings, allowing it to interact with dark matter in subtle ways. Others suggest that dark energy is a property of the vacuum itself, arising from quantum fluctuations that permeate all of space. These fluctuations, though tiny, could collectively exert a repulsive force, driving the universe's acceleration. These hypotheses remain unproven, but they hint at a deeper connection between the visible and invisible components of the universe. Known, dark matter comprises approximately 27% of the universe, while dark energy accounts for 68%. Together, they outweigh visible matter by a factor of 5. This means that for every atom of hydrogen, helium, or any other element that makes up stars, planets, and life itself, there are 5 times as many particles of dark matter exerting their influence. Dark energy's repulsive force is so powerful that it doubles the distance between galaxy clusters every 10 billion years, a timescale that dwarfs the age of the Earth. Unknown. The nature of dark matter particles and the origin of dark energy remain mysterious. Despite decades of research, scientists have yet to directly detect dark matter particles or identify their properties. Dark energy is even more elusive, its existence inferred solely from its effects on the universe's expansion. Some researchers question whether dark energy is a constant force or if it varies over time, a possibility that could radically alter our understanding of the universe's fate. To be continued. Part 4. The Stellar Cycle. What if every star is a story of birth, life, and death? In the vast, silent expanse of the cosmos, stars are more than just points of light. They are living entities, born from the ashes of their predecessors, shining brilliantly for eons, and ultimately succumbing to their own inevitable demise. Observation. Stars are not eternal. They are born in vast clouds of gas and dust, known as nebulae, which are the stellar nurseries of the universe. These nebulae, such as the Orion Nebula, located some 1,344 light-years away from Earth, are sites of intense star formation, where gravity pulls together clumps of matter that ignite into new stars. Our Sun, a medium-sized star of about 1.4 million kilometers in diameter, is currently in its stable main sequence phase, fusing hydrogen into helium in its core, a process that has been ongoing for approximately 4.6 billion years. The life of a star is a delicate balance between gravity and nuclear fusion. In its main sequence phase, a star like the Sun generates energy by converting hydrogen into helium, releasing light and heat in the process. This energy counteracts the force of gravity, which would otherwise cause the star to collapse under its own weight. However, this balance cannot last forever. As the hydrogen fuel in the core is depleted, the star begins to change, setting the stage for the next act in its cosmic drama. Interpretation. The life cycle of a star depends on its mass. Low-mass stars like our Sun will eventually swell into red giants, expanding to hundreds of times their original size as they begin to fuse helium into heavier elements. During this phase, the star's outer layers become unstable and are shed into space, forming a planetary nebula. What remains is a dense, Earth-sized white dwarf, a stellar corpse that slowly cools over billions of years. For example, the star Betelgeuse, a red supergiant in the constellation Orion, is nearing the end of its life and will likely explode as a supernova within the next 100,000 years. Massive stars, on the other hand, meet their end in catastrophic supernova explosions. These events release enormous amounts of energy, as much as the total output of an entire galaxy, and scatter heavy elements like carbon, oxygen, and iron into the cosmos. These elements, forged in the hearts of stars, are the building blocks of planets and life itself. One such supernova, SN 1987A, occurred in the Large Magellanic Cloud, a neighboring galaxy of the Milky Way, and was visible to the naked eye in 1987. Speculation. Could life exist around other stars? The search for exoplanets, planets orbiting stars outside our solar system, has revealed thousands of worlds, some of which lie within the habitable zones of their parent stars. In these regions, temperatures could allow liquid water to exist on the surface, a key ingredient for life as we know it. NASA's Kepler Space Telescope, launched in 2009, identified over 2,600 confirmed exoplanets during its mission, revolutionizing our understanding of planetary systems. Yet, the conditions for life are complex, requiring not just water, but also a stable atmosphere, a magnetic field to shield against harmful radiation, and perhaps even a moon to stabilize the planet's axial tilt, as is the case with Earth and its moon. The quest to find such worlds, and to understand whether life has emerged elsewhere, continues with missions like the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope, JWST. TESS, launched in 2018, is designed to search for exoplanets around the closest and brightest stars, providing prime targets for follow-up observations. The JWST, launched in 2021, will use its advanced infrared capabilities to study the atmospheres of exoplanets, searching for signs of water vapor, oxygen, and other potential biosignatures. Known stars undergo a predictable life cycle based on their mass, from birth in nebulae to death as white dwarfs or supernovae. The discovery of exoplanets has expanded our understanding of planetary systems and the potential for life beyond Earth. Unknown. The exact conditions required for life to emerge on exoplanets remain uncertain, though habitable zones offer a starting point for exploration. The search for biosignatures in exoplanet atmospheres is still in its early stages, and definitive evidence of extraterrestrial life has yet to be found. To be continued. Part 5. The Black Abyss. Are black holes gateways to other realities? This question has fascinated scientists and dreamers for decades, as black holes challenge our understanding of physics and reality. The concept of a black hole was first proposed in the 18th century by English natural philosopher John Michell, who contemplated dark stars from which light could not escape. However, it wasn't until the 20th century that black holes became a cornerstone of astrophysics, thanks to Albert Einstein's theory of general relativity. Observation. Black holes are areas of space-time with gravity so intense that nothing, not even light, escapes. They form when massive stars, 20 to 25 times the Sun's mass, collapse into a singularity, an infinitely dense point surrounded by an event horizon. The nearest known black hole, Gaia BH1, discovered in 2022, is about 1,560 light-years away, highlighting the cosmos's vastness. This black hole is approximately 10 times the mass of the Sun, making it one of the smallest known black holes and a critical reference point for studying these phenomena. The event horizon is not a physical surface, but a region where escape velocity exceeds light speed, making it a cosmic abyss. The first black hole, Cygnus X1, was identified in 1964 via X-ray emissions, showcasing advancements in astronomical observation. Cygnus X1 is part of a binary star system, where it pulls matter from its companion star, creating a spectacular display of X-ray emissions as the matter accelerates and heats up before disappearing into the black hole. Interpretation. Black holes are not just cosmic graveyards. They are engines of creation. Matter falling into a black hole forms an accretion disk, emitting radiation across the electromagnetic spectrum. This energy output can outshine entire galaxies, making black holes the brightest objects in the universe. The accretion disk's temperature can reach millions of degrees, generating intense X-rays and gamma rays that illuminate the cosmos. The Milky Way's supermassive black hole, Sagittarius A, has a mass 4 million times that of the Sun. Such cosmic titans are found in nearly all large galaxies, influencing star formation, galactic structure, and dark matter distribution. Sagittarius A is relatively quiet compared to other supermassive black holes, but occasional flares from its accretion disk remind us of its latent power. Speculation: what lies beyond the event horizon? Theories suggest black holes could be portals to other universes or white holes, though white holes remain hypothetical. Some proposed the singularity could be a gateway to higher dimensions, where known physics breaks down. These ideas stem from string theory and loop quantum gravity, which explore the multi-dimensional structure of space-time. In string theory, black holes could be composed of intersecting strings and membranes, offering a glimpse into a reality where extra dimensions are as fundamental as length, width, and height. Black holes might also relate to the holographic principle, suggesting our 3D universe is a projection of information on a 2D boundary. The event horizon could act as a cosmic hologram, storing the universe's history in compressed form. This principle, derived from the work of physicists Gerard 't Hooft and Leonard Susskind, challenges our understanding of space, time, and information, hinting at a deeper layer of reality encoded on the event horizon surface. Observations of gravitational waves first detected in 2015 have revealed more about black hole behavior. The Event Horizon Telescope captured the first black hole image in 2019, focusing on the supermassive black hole in galaxy M87. This milestone advanced our understanding of these enigmatic objects. The image, a fiery ring of light surrounding a dark center, captivated the world and provided visual evidence of the event horizon's existence. Since then, the Event Horizon Telescope has continued to refine its observations, offering sharper images and more detailed data about black hole dynamics. Known: black holes are regions where gravity is so strong that light cannot escape. They form from collapsing massive stars and play a critical role in galactic evolution. Their presence can shape the structure of galaxies, regulate star formation, and even influence the distribution of dark matter. Unknown: the nature of the singularity and the fate of matter crossing the event horizon remain mysterious. The existence of white holes and higher dimensions are speculative. While black holes are deeply connected to the fabric of space-time, their true nature and the secrets they hold may forever elude us, hidden behind the veil of the event horizon. Part 6. The Galactic Dance. What if galaxies are not just islands of stars, but living ecosystems? Observation: galaxies are not static objects. They interact, merge, and evolve over cosmic timescales. Our own Milky Way, a spiral galaxy containing between 100 and 400 billion stars, is on a collision course with the Andromeda Galaxy, a similar spiral galaxy located 2.5 million light-years away. In about 4 billion years, the two will merge into a single larger galaxy, dubbed Milkomeda by astronomers. This future collision is not an isolated event. The Hubble Space Telescope has captured images of galaxies in various stages of interaction, from gentle gravitational tugs to full-blown mergers. These cosmic dances can last hundreds of millions of years, transforming the galaxies involved into new, unified structures. The night sky will slowly change as Andromeda approaches. Currently, Andromeda is visible as a faint smudge in the night sky, but in approximately 3.75 billion years, it will loom large, appearing as a brilliant glow that stretches across our horizon. The merger will not be a catastrophic event for most stars. The distances between stars are so vast that direct collisions are extremely rare. Instead, the merger will create a spectacular light show as gravitational forces compress gas and dust, igniting bursts of star formation. These newborn stars will illuminate the merging galaxies, painting the cosmos with streaks of blue and pink light. Interpretation. Galactic interactions are driven by gravity, the universal force that binds matter together. When galaxies collide, their stars rarely crash into one another due to the vast distances between them. Instead, the galaxies' shapes are distorted, and new stars are born in the compressed gas and dust. These interactions can trigger bursts of star formation, creating entire generations of new worlds. For example, the Antennae galaxies, located about 68 million light-years away, are in the process of merging. Their interaction has sparked the formation of millions of new stars, many of which are massive and short-lived, ending their lives in supernova explosions. These explosions distribute heavy elements into the cosmos, enriching the interstellar medium and laying the groundwork for future generations of stars and planets. The gravitational dance of galaxies can also lead to the formation of new structures, such as tidal tails and bridges. These features are created when the gravitational forces of interacting galaxies pull stars, gas and dust into elongated streams. The Magellanic Stream, a vast cloud of gas stretching between the large and small Magellanic Clouds, is an example of this process. Spanning over 200,000 light-years, this stream is a testament to the power of galactic interactions to shape the cosmos. Speculation. Could galactic mergers be the key to understanding the universe's large-scale structure? Some theories suggest that the distribution of galaxies in the cosmos is not random, but follows a pattern dictated by dark matter and dark energy. By studying the aftermath of galactic collisions, astronomers hope to unravel the mysteries of these invisible forces and gain insight into the cosmic web that connects all matter in the universe. For instance, the Bullet Cluster, a system of two colliding galaxy clusters, provides evidence for the existence of dark matter. The visible matter in these clusters, primarily hot gas, has been separated from the dark matter during the collision, allowing astronomers to map the distribution of dark matter through gravitational lensing. The study of galactic interactions also offers clues about the nature of dark energy. The accelerating expansion of the universe, driven by dark energy, influences the frequency and outcomes of galactic mergers. By comparing the rates of mergers in the distant past to those in the present, astronomers can test models of dark energy and refine their understanding of its role in cosmic evolution. Known. Galaxies interact and merge, driven by gravitational forces leading to star formation and structural changes. The Milky Way and Andromeda galaxies are on a collision course, expected to merge in about 4 billion years. Galactic interactions can create tidal tails, bridges, and other structures, shaping the cosmos in profound ways. Unknown. The exact role of dark matter and dark energy in shaping the large-scale structure of the universe remains unclear. The long-term effects of galactic mergers on the evolution of stars, planets, and life itself are still subjects of ongoing research. Part 7. The Nebulae Nurseries. What if nebulae are the cosmic cradles of life? Imagine drifting through the cosmos, where light takes years to traverse the vast emptiness, and suddenly encountering a glowing, ethereal cloud that stretches across tens of light years. These are the nebulae, the universe's nurseries where stars are born and worlds take shape. Observation. Nebulae are vast clouds of gas and dust, the birthplaces of stars and planets. They come in many forms, from the glowing emission nebulae illuminated by nearby stars to the dark, dusty clouds that obscure background light. The Orion Nebula, the most famous of these, is visible to the naked eye as a faint smudge in the constellation Orion. Spanning over 24 light-years, it is a bustling stellar nursery, home to more than 700 stars in various stages of formation. Telescopes reveal its intricate structure, swirling tendrils of gas sculpted by the intense radiation and stellar winds of its newest inhabitants. The Eagle Nebula, another iconic example, showcases towering pillars of gas and dust, each several light-years tall. These pillars of creation, as they are known, are being slowly eroded by the ultraviolet light of nearby massive stars. Yet within these pillars, denser regions collapse under their own gravity, giving birth to new stars. The Hubble Space Telescope has captured these structures in stunning detail, revealing the dynamic interplay between creation and destruction in these cosmic nurseries. Interpretation. Nebulae are not just beautiful celestial objects, they are the engines of cosmic creation. Within their dense cores, gravity compresses gas and dust, igniting the nuclear fusion reactions that give birth to stars. The temperature in these cores can reach 10 million degrees Celsius, hot enough to fuse hydrogen atoms into helium, releasing the energy that makes stars shine. As these new stars form, they sculpt the surrounding material, creating intricate structures that can span light years. Over time, the radiation and winds from these stars disperse the remaining gas and dust, revealing newly formed planets and moons. The process is not always gentle. Massive stars, which form in the densest regions of nebulae, live fast and die young. Their intense radiation and powerful winds carve out cavities in the nebula, pushing gas and dust outward like a cosmic snowplow. When these stars reach the end of their lives, they explode as supernovae, releasing enormous amounts of energy and heavy elements into the surrounding nebula. These explosions can trigger the collapse of nearby gas clouds, sparking a new wave of star formation. Speculation. Could nebulae hold the key to understanding the origin of life? The complex molecules found in these cosmic clouds, including organic compounds like polycyclic aromatic hydrocarbons, PAHs, suggest that the building blocks of life may be forged in the crucibles of star formation. As stars and planets emerge from the nebulae, these molecules could be incorporated into their atmospheres and surfaces, providing the raw materials for life to take root. In the Murchison meteorite, which fell to Earth in 1969, scientists discovered over 70 different amino acids, the building blocks of proteins. These molecules are believed to have formed in the interstellar medium, possibly within a nebula, before being incorporated into the meteorite's parent asteroid. If such complex molecules can form in nebulae, it raises the tantalizing possibility that the seeds of life are scattered throughout the universe, waiting for the right conditions to grow. Observations of the Orion Nebula have revealed the presence of water vapor, as well as organic molecules like methanol and formaldehyde. These molecules are found in the dense, star-forming regions of the nebula, where they could potentially be incorporated into forming planets. The discovery of these molecules supports the idea that nebulae are not just stellar nurseries but also chemical factories, producing the ingredients necessary for life. Known, nebulae are regions of gas and dust where stars and planets are born. Their dense cores provide the conditions necessary for star formation, while their intricate structures are shaped by the interplay of gravity, radiation, and stellar winds. Unknown. The exact mechanisms by which complex organic molecules form in nebulae and their role in the origin of life remain areas of active research. While it is clear that nebulae contain the building blocks of life, the question of how these molecules are incorporated into planets and whether they contribute to the emergence of life is still unanswered. To be continued. Part 8. The Cosmic Lighthouses. What if quasars are beacons from the dawn of time? These enigmatic objects, first identified in the 1960s, have captivated astronomers with their astonishing luminosity, outshining entire galaxies and acting as cosmic searchlights that illuminate the distant past. At the heart of every quasar lies a supermassive black hole, an object so dense that not even light can escape its gravitational pull. These black holes, ranging from millions to billions of times the mass of the Sun, are surrounded by accretion disks, swirling vortices of gas and dust that heat up to extreme temperatures as they spiral inward, releasing energy that propels jets of plasma and radiation outward at relativistic speeds. Observation. Quasars are the brightest objects in the universe, emitting more light than entire galaxies. They are powered by supermassive black holes at the centers of distant galaxies, where matter falling into the black hole's gravitational well releases enormous amounts of energy. This energy is emitted as radiation across the electromagnetic spectrum, from radio waves to X-rays. Some quasars are so distant that their light has taken over 13 billion years to reach us, offering a glimpse into a time when the universe was less than 1 billion years old. Their light, redshifted by the expansion of the cosmos, reveals the chemical signatures of hydrogen, helium, and heavier elements formed in the furnaces of the first stars. The most luminous quasars can emit as much energy in a single day as the Sun does in 10 billion years. One such example is the quasar 3C273, located in the constellation Virgo, which was among the first quasars identified. Its jet of plasma extends over 200,000 light-years, dwarfing the Milky Way in scale. Another quasar, SDSS JWO 100 Pl 2802, is so distant that its light has been travelling for 12.9 billion years, providing insight into a time when the universe was just 875 million years old. Interpretation. Quasars are not just cosmic curiosities, they are windows into the early universe. Because they are so bright, quasars can be observed from billions of light-years away, allowing astronomers to study the conditions of the universe when it was just a fraction of its current age. By analyzing the light from quasars, scientists can determine the composition of the intergalactic medium, the distribution of matter in the cosmos, and even the expansion rate of the universe. For instance, the absorption lines in quasar spectra reveal the presence of neutral hydrogen gas in the intergalactic medium, which helps trace the structure of the cosmic web, a vast network of filaments and voids that permeates the universe. Quasars also serve as markers of cosmic time. Their redshifts, caused by the expansion of the universe, allow astronomers to map the distribution of galaxies and dark matter over cosmic history. The Sloan Digital Sky Survey, which has catalogued over 1 million quasars, has been instrumental in creating three-dimensional maps of the universe, revealing the large-scale structure of the cosmos on scales of billions of light-years. These maps show how galaxies cluster together in filaments and sheets, surrounded by vast voids like a cosmic foam. Speculation. Could quasars be the key to understanding the evolution of galaxies? Some theories suggest that the intense radiation and winds from quasars could regulate star formation, blowing away gas and dust that would otherwise collapse to form new stars. This process, known as quasar feedback, could explain why some galaxies are more active than others, and why the rate of star formation in the universe has declined over time. For example, in galaxies with active quasars, the powerful outflows of gas and dust driven by the black hole's activity can suppress star formation, leading to the quenching of galaxies. This mechanism may have played a crucial role in shaping the galaxies we see today, including our own Milky Way. The role of quasars in galactic evolution is further complicated by their intermittent nature. Quasars are not constant beacons. They flicker on and off over millions of years as the supermassive black hole at their center accretes matter. This variability means that quasar feedback may not be a continuous process, but rather a series of episodic events that shape the galaxy over time. Understanding these cycles of activity could shed light on the complex interplay between black holes and their host galaxies. Known. Quasars are powered by supermassive black holes and emit radiation across the electromagnetic spectrum. Their light provides a window into the early universe, revealing the composition and structure of the cosmos. Unknown. The role of quasar feedback in regulating star formation and galactic evolution remains an area of ongoing research. The precise mechanisms by which quasars influence their host galaxies and the timescales over which these processes occur are still not fully understood. To be continued. Part 9. The Ripples of Space-Time. What if the universe is a symphony of gravitational waves? Every moment, unheard and unseen, the cosmos resonates with faint vibrations from colliding black holes, merging neutron stars, and echoes of the Big Bang. These ripples in space-time, predicted by Einstein in 1916, were thought too faint to detect. But on September 14, 2015, at 5:51 a.m. EDT, the universe shared its secrets with humanity for the first time. In the quiet of the Louisiana and Washington State observatories, LIGO's detectors twitched, a minuscule disturbance lasting just 0.2 seconds but carrying the weight of cosmic history. Observation. Gravitational waves are distortions in space-time caused by the acceleration of massive objects. LIGO first detected these ripples, a faint chirp from two merging black holes over 1.3 billion light-years away. Each black hole was roughly 30 times the Sun's mass, and their collision released 50 times more energy than all observable stars combined, briefly radiating 3.6 x 10^49 watts, more than the entire visible universe. This cataclysmic event sent gravitational waves traveling at light speed, subtly stretching and squeezing space-time as they passed through Earth, warping the 4-kilometer-long arms of LIGO's interferometers by less than the width of a proton. This discovery ushered in a new era of astronomy. For the first time, scientists could observe the universe using gravity, not just light. Gravitational waves traverse the cosmos unimpeded, unlike electromagnetic radiation, which can be absorbed or scattered. They provide astronomers with an unparalleled tool to explore the universe's most mysterious objects, hidden behind veils of dust, gas, or sheer distance. Since 2015, LIGO and Virgo have recorded dozens of gravitational wave events. Each tells a story of cosmic violence, black holes merging, neutron stars colliding, or even the faint hum of the Big Bang. One event, GW170817, was groundbreaking. On August 17, 2017, LIGO and Virgo detected gravitational waves from two merging neutron stars, each about 1.4 times the Sun's mass. Located 130 million light-years away, this event was also observed by traditional telescopes, marking the first detection of an event in both light and gravitational waves. The resulting explosion, a kilonova, glowed brightly in ultraviolet, optical and infrared wavelengths, offering a complete picture of the event's aftermath. Interpretation. Gravitational waves offer more than cosmic curiosities. They provide a new way to observe the universe. GW170817 confirmed that gravitational waves travel at light speed, ruling out alternative theories of gravity. It also revealed the origins of heavy elements like gold and platinum forged in neutron star mergers. By studying these waves, astronomers can explore black hole event horizons, neutron star interiors, and even the Big Bang itself. Gravitational waves also offer a unique window into the early universe. The cosmic microwave background, CMB, provides a snapshot of the universe 380,000 years after the Big Bang. However, gravitational waves could allow astronomers to peer further back, to the first 10^36 seconds after the Big Bang. During this inflationary period, the universe underwent rapid expansion, producing a background of gravitational waves. Detecting these waves could reveal the universe's earliest moments, when the fundamental forces of nature began to take shape. Speculation. Could gravitational waves help us understand the universe's mysterious dark sector? Some theories suggest dark matter and dark energy, which make up 95% of the universe's energy content, could interact with gravitational waves. These interactions might leave faint imprints on detected signals, such as slight distortions from dark matter scattering or frequency shifts from dark energy's gravitational redshift. Analyzing these imprints could provide insights into dark matter and dark energy. Current detectors lack the sensitivity to measure these effects, but future observatories like LISA or the Einstein telescope could revolutionize our understanding. These instruments would detect gravitational waves with greater precision and at lower frequencies, where signals from supermassive black holes in the early universe reside. LISA, for instance, would consist of 3 spacecraft orbiting the Sun in a triangular formation, separated by 2.5 million kilometers, sensitive to frequencies as low as 0.1 millihertz, a range inaccessible from Earth. Part 10, The Search for Other Earths. What if the universe is teeming with worlds like ours? Imagine gazing into the night sky, knowing that countless planets orbit distant stars, some potentially harboring life. This question, once purely philosophical, has become a driving force in modern astronomy. Observation. Exoplanets, planets orbiting other stars, are ubiquitous in the cosmos. Since the first confirmed discovery in 1995, astronomers have identified over 5,000 exoplanets, ranging from gas giants larger than Jupiter to rocky worlds smaller than Earth. Many of these planets orbit within their stars' habitable zones, the regions where liquid water could theoretically exist on their surfaces. This is critical, as water is considered essential for life as we know it. For instance, the TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets, with 3 firmly in the habitable zone. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet detection. During its 9-year mission, Kepler identified over 2,600 confirmed exoplanets, revealing that, on average, every star in the Milky Way hosts at least one planet. Its successor, the Transiting Exoplanet Survey satellite TESS, launched in 2018, has already discovered over 200 exoplanets and is expected to find thousands more in the coming years. These telescopes use the transit method, detecting the slight dimming of a star's light as a planet passes in front of it. Interpretation. The discovery of exoplanets has revolutionized our understanding of the universe and our place within it. No longer are we limited to the 8 planets of our solar system. We now know that planetary systems are the norm, not the exception. By studying the atmospheres, compositions, and orbits of exoplanets, astronomers hope to uncover the conditions necessary for life to emerge and thrive beyond Earth. For example, the study of planetary atmospheres through spectroscopy allows scientists to detect the presence of specific gases such as oxygen, methane, and water vapor, which could indicate the presence of life. The diversity of exoplanets is astonishing. From hot Jupiters that orbit their stars in mere days to super-Earths, with masses greater than Earth but smaller than ice giants like Neptune. The variety challenges our understanding of planetary formation. Some exoplanets, like HD 189733b, are so close to their stars that they experience temperatures exceeding 1,000 degrees Celsius and have winds blowing at thousands of kilometers per hour. Others, like Kepler 442b, are so Earth-like in size and orbit that they are considered prime candidates for habitability. Speculation. Could one of these exoplanets be home to extraterrestrial life? The search for biosignatures, chemical indicators of life such as oxygen and methane, in the atmospheres of exoplanets is a rapidly growing field. If even one exoplanet is found to harbour life, it would be a monumental discovery, proving that life is not unique to Earth and that the universe is teeming with living worlds. Future missions, such as the James Webb Space Telescope, JWST, and the European Extremely Large Telescope, EELT, will be instrumental in this search. The JWST, launched in 2021, will use its advanced infrared capabilities to study the atmospheres of exoplanets in unprecedented detail. The prospect of finding life beyond Earth is not just a scientific curiosity. It has profound philosophical and cultural implications. It would challenge our understanding of our place in the universe and force us to reconsider our relationship with the cosmos. The discovery of extraterrestrial life, even in its simplest form, would be a turning point in human history, akin to Copernicus's realization that Earth is not the center of the universe. Known, exoplanets are common in the universe, with thousands discovered to date. The diversity of exoplanets is vast, ranging from gas giants to rocky worlds, some of which orbit within their stars' habitable zones. Unknown, the presence of life on exoplanets remains unconfirmed, though the search for biosignatures continues. Future missions like the James Webb Space Telescope and the European Extremely Large Telescope will play crucial roles in this quest. To be continued. Part 11. The Silent Cosmos. What if we are not alone, but the universe is too vast to hear us? The cosmos stretches out in every direction, a staggering 93 billion light-years across, filled with an estimated 2 trillion galaxies, each containing hundreds of billions of stars on average. The numbers are almost incomprehensible, yet they represent the stage on which the drama of life, intelligent or otherwise, plays out. Observation. The search for extraterrestrial intelligence, SETI, has been ongoing for decades, with scientists scanning the skies for signs of advanced civilizations. From Frank Drake's pioneering Project Ozma in 1960, which listened for signals from 2 nearby stars, to modern projects like Breakthrough Listen, the quest to detect artificial signals from space has yielded no definitive results, a conundrum known as the Great Silence. Breakthrough Listen, launched in 2015 with a $100 million funding commitment over 10 years, is the most comprehensive SETI project to date, surveying millions of stars and even targeting specific exoplanets like those in the TRAPPIST-1 system. Yet, the silence persists, a cosmic enigma that deepens with each passing year. The WOW signal, detected in 1977 by the Big Ear radio telescope in Ohio, remains one of the most intriguing anomalies in SETI history. Lasting for 72 seconds, the narrowband radio signal appeared to come from the direction of the constellation Sagittarius. Despite numerous attempts to replicate the detection, the signal has never been observed again. It stands as a singular, unexplained event, a tantalizing hint that perhaps, somewhere out there, another intelligence exists. Interpretation. The absence of evidence is not evidence of absence. The sheer scale of the universe, with its hundreds of billions of stars and countless planets, means that any signal we detect would have to travel vast distances to reach us. Light, the fastest messenger in the cosmos, takes 2.5 million years to traverse the distance between our Milky Way galaxy and its nearest neighbor, Andromeda. Any signal from a civilization within Andromeda would be a temporal snapshot, a message from deep in the past. Moreover, civilizations may rise and fall in the blink of a cosmic eye. Our own human civilization has existed for mere thousands of years, a fleeting moment compared to the billions of years of cosmic evolution. The lifespan of civilizations may be relatively short compared to cosmic timescales, making the likelihood of 2 civilizations overlapping in time and space exceedingly rare. This is the essence of the rare Earth hypothesis, which posits that the emergence of intelligent life may be an extraordinarily uncommon event in the universe. Speculation. Could the Great Silence be a reflection of our own limitations? Perhaps our search methods are too narrow, focused on technologies like radio waves that may be obsolete or irrelevant to advanced civilizations. We assume that extraterrestrial intelligences would use communication methods similar to ours, but this may be a profoundly anthropocentric viewpoint. Advanced civilizations might employ technologies beyond our comprehension, communicating through methods that are as inscrutable to us as a smartphone would be to an ancient Roman. Alternatively, extraterrestrial life may exist in forms so different from our own that we fail to recognize it. Life on Earth is based on carbon and relies on liquid water as a solvent, but other forms of biochemistry are theoretically possible. Silicon-based life, for example, has been proposed as an alternative, with selenes, silicon-hydrogen compounds, taking the place of hydrocarbons. Such life might exist under conditions vastly different from those on Earth, perhaps in the dense atmospheres of gas giants, or within the icy oceans of moons like Europa, or Enceladus. The search for life, intelligent or otherwise, remains one of the greatest challenges and mysteries of modern science. As we continue to explore the cosmos, we are driven by a profound curiosity, a desire to know whether we are alone in the universe. Each new discovery, from the detection of exoplanets to the exploration of potentially habitable worlds within our own solar system, brings us closer to answering this fundamental question. Yet the great silence persists, a cosmic riddle that challenges our understanding of the universe and our place within it. Known. The search for extraterrestrial intelligence has yielded no definitive results to date. Our own civilization has been detectable via radio waves for less than a century, a mere blink of an eye on cosmic timescales. The Arecibo message, broadcast in 1974, was a powerful radio signal sent toward the globular star cluster M13, but it will take 25,000 years to arrive, highlighting the vast distances involved in interstellar communication. Unknown, the nature of extraterrestrial life and the likelihood of its existence remain open questions. We do not know if life is a common feature of the universe or an exceedingly rare phenomenon. The Fermi paradox, which asks, "Where is everybody?" underscores the tension between the high probability of extraterrestrial life and the lack of evidence for it. As we continue to search, we are left to wonder whether the great silence is a sign of our solitude or a testament to the vastness and mystery of the cosmos. To be continued. Part 12. The Familiar Strangers. What if the secrets of the universe lie closer than we think? Our solar system, a mere speck in the cosmic landscape, might hold the clues we seek. It is a place of profound familiarity. We have named its planets, charted their orbits, and even walked on one of its worlds. But it is also a realm of enduring mystery, where every answer begets more questions. Observation. Our solar system, once thought to be the center of the cosmos, is now known to be just one of countless planetary systems in the universe. Yet it remains a treasure trove of mysteries, from the fiery surface of the sun to the icy moons of the outer planets. Mars, with its rust-red surface, is pockmarked with craters and carved by ancient rivers that speak of a warmer, wetter past. The gas giants, Jupiter and Saturn, are storm-racked colossi, their swirling atmospheres concealing layer upon layer of mystery. Beyond them lie the ice giants Uranus and Neptune, their deep blue hues hinting at frigid, enigmatic depths. Scattered throughout are the moons, 80 at Jupiter alone, 83 at Saturn, each a small world in its own right, some with atmospheres, oceans, or even the building blocks of life. The solar system is not just a collection of celestial bodies. It is a dynamic ecosystem shaped by gravity, radiation, and the interplay of elements. Mars' thin atmosphere, composed mostly of carbon dioxide, bears the scars of solar wind stripping, a process that may have robbed it of much of its former warmth. Yet, its polar ice caps, composed of water ice and dry ice, still grow and shrink with the seasons. On Jupiter's moon Io, over 400 active volcanoes spew sulphurous lava onto the surface, driven by the tidal forces of Jupiter and the other Galilean moons. Saturn's rings are ever-changing structures, sculpted by the gravity of the planet and its moons. Interpretation. The planets of our solar system are not static objects but dynamic worlds shaped by the forces of nature. Mars hints at a past where liquid water flowed freely, its surface bearing the remnants of deltas and lake beds. Jupiter's moon, Europa, with its subsurface ocean, is a prime candidate for harboring extraterrestrial life. Its icy shell, crisscrossed by reddish fractures, suggests a complex interplay between the moon's interior and the harsh radiation from Jupiter. Saturn's moon Titan, with its lakes of methane, offers a glimpse into an alien chemistry unlike anything on Earth. Its dense, nitrogen-rich atmosphere is filled with organic compounds, raining down onto a surface shaped by rivers and seas of liquid hydrocarbons. The solar system is not just a museum of ancient history. It is a living laboratory of planetary evolution. Pluto, reclassified as a dwarf planet, reveals a world far more geologically active than expected. The New Horizons spacecraft sent back images of a heart-shaped glacier named Sputnik Planitia, a vast nitrogen ice plain that may hide a subsurface ocean. Even the asteroid belt is a fossil record of the early solar system. The Japanese Hayabusa 2 mission found evidence of water and organic compounds on the asteroid Ryugu, hinting that such bodies may have seeded Earth with the ingredients for life. Speculation. Could the moons of the outer planets be the key to understanding the origins of life? Some theories suggest that life may have emerged not on Earth but on Mars or Europa, carried to our planet by meteorites. If life exists elsewhere in the solar system, it could shed light on the universal principles governing the emergence of complexity and consciousness. Europa's subsurface ocean, rich in salts and minerals, may be the most promising habitat for life beyond Earth. Future missions such as NASA's Europa Clipper aim to explore this moon in detail, searching for signs of biology in its icy plumes and subsurface ocean. Saturn's moon Enceladus is one of the most geologically active bodies in the solar system. Its southern polar region is marked by tiger stripes, deep fissures that spew geysers of water vapor and ice particles into space. These plumes, sampled by the Cassini spacecraft, were found to contain organic compounds, hinting at a subsurface ocean that may harbor life. Even Titan, despite its frigid temperatures, is a world of astrobiological interest. Its methane-based chemistry could provide insights into how life might arise in environments vastly different from our own. The solar system is home to a diverse array of worlds, including planets, moons, and asteroids, each with unique characteristics. From the scorching surface of Venus to the distant Oort cloud, every corner of the solar system tells a different story. The planets and moons are not isolated entities, but interconnected pieces of a cosmic puzzle, shaped by gravitational tugs, collisions, and the relentless forces of nature. The presence of life beyond Earth within the solar system remains unconfirmed, though several moons are considered promising candidates. Europa, Enceladus, and Titan are at the forefront of this search, but even the planets themselves are not ruled out. Venus may have habitable zones in its upper atmosphere. Mars continues to captivate scientists and the public alike with its potential for past or present microbial life. As we send more sophisticated probes and rovers to these worlds, the question of whether we are alone in the solar system inches closer to an answer. Part 13. The Sun's Fury. What if the star that gives us life could also take it away? The Sun, a blazing furnace 93 million miles from Earth, is the lifeblood of our planet, yet its temperamental nature could unleash catastrophic consequences. Observation. The Sun is the engine of our solar system, providing the light and heat that make life possible. It churns with unimaginable energy, releasing the equivalent of 91.5 billion megatons of TNT every second. Yet it is also a dynamic and unpredictable star, prone to violent outbursts of energy. Solar flares, which are sudden flashes of brightness, can release as much energy as 160 billion megatons of TNT in mere minutes. Coronal mass ejections, CMEs, on the other hand, are massive clouds of magnetized plasma that erupt from the Sun's outer layer, hurtling billions of tons of material into space at speeds of up to 3 million miles per hour. These events can interact with Earth's magnetic field and atmosphere, producing stunning auroras but also wreaking havoc on our technology. The Sun's surface is a turbulent landscape of plasma rivers and magnetic fields. Sunspots, dark regions that appear as cooler areas on the Sun's surface, are often the sites of intense magnetic activity. These spots can grow to be larger than Earth, and their magnetic fields can become twisted and tangled, leading to explosive releases of energy. The largest sunspot ever recorded in April 1947 was estimated to be over 18 billion square kilometers, large enough to swallow the entire Earth with room to spare. On average, the Sun's surface temperature is about 5,500 degrees Celsius, but during a solar flare, temperatures can soar to 10 million degrees Celsius or more in the corona, the Sun's outer atmosphere. Interpretation, solar activity follows an 11-year cycle during which the number of sunspots increases and decreases. This cycle, first observed by astronomer Samuel Heinrich Schwabe in 1843, is a rhythmic pulsation of the Sun's magnetic field. At the peak of the cycle, known as the solar maximum, solar flares and CMEs are more frequent and intense. During this phase, the Sun's magnetic poles reverse, with the North Pole becoming the South and vice versa. This magnetic flip occurs roughly every 11 years, though the exact timing can vary. At the solar minimum, the Sun is quieter, but even during this phase, it can unleash powerful storms. Solar storms pose a significant threat to modern technology. Satellites, which are essential for communication, navigation, and scientific research, are particularly vulnerable. A direct hit from a CME can induce electrical currents in a satellite's systems, damaging or even destroying its electronics. In March 1989, a powerful solar storm caused a 9-hour blackout in Quebec, Canada, leaving millions without power. The storm also disrupted radio communications and caused satellites to malfunction. The economic cost of such an event today could be staggering, with estimates suggesting that a severe solar storm could cause up to $2 trillion in damages in the United States alone. The Carrington event of 1859 remains the most powerful solar storm on record. Named after British astronomer Richard Carrington, who observed the storm's associated solar flare, the event caused worldwide disruptions in telegraph systems. Telegraph operators reported sparks leaping from their equipment, and some even received electric shocks. The storm's auroras, typically confined to polar regions, were visible as far south as the Caribbean and Hawaii. If a storm of this magnitude were to occur today, its impact would be far more devastating due to our reliance on electricity and technology. Speculation. Could a future solar storm be even more devastating? As our reliance on technology grows, so too does our vulnerability to space weather. A severe solar storm could cripple modern infrastructure, from GPS systems to the internet, and cause widespread blackouts lasting weeks or months. Understanding and predicting solar activity is therefore crucial for safeguarding our technological civilization. NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar Orbiter are among the spacecraft currently studying the Sun, providing scientists with unprecedented data to improve forecasting models. The Sun's behavior is notoriously unpredictable, and its cycles can vary in intensity. In 2019, researchers discovered that the Sun's magnetic field undergoes a terminator event every 11 years, which marks the end of one solar cycle and the beginning of another. This event is characterized by a sudden weakening of the Sun's magnetic bands, which wrap around the star like a ribbon. Understanding these events could help scientists predict the timing and strength of future solar cycles, giving us a better chance to prepare for the Sun's fury. Known, solar activity follows an 11-year cycle, with peaks in sunspot numbers and solar flares. The Sun's magnetic field reverses during the solar maximum, and CMEs can induce electrical currents in Earth's infrastructure. Unknown. The exact mechanisms driving solar activity and the potential impact of future solar storms remain areas of active research. The timing and severity of the Sun's terminator events are still not fully understood. To be continued. Part 14. The Human Frontier. What if our future lies beyond the boundaries of Earth? The vast expanse of space beckons not just as a realm of scientific discovery, but as a potential new home for humanity. This question is not merely philosophical, it is a driving force behind the most ambitious engineering and scientific endeavors of our time. Every launch, every rover deployed, and every satellite placed into orbit brings us closer to answering it. Observation. Space exploration has come a long way since the launch of Sputnik in 1957. From the Apollo missions to the Moon to the International Space Station, ISS, humanity has steadily pushed the boundaries of what is possible. The Apollo program alone cost $25.4 billion, over $150 billion in today's dollars, and employed over 400,000 people at its peak, demonstrating the scale of investment required to reach beyond our planet. Today, private companies like SpaceX and Blue Origin are leading the charge toward a new era of space travel, with plans to send humans to Mars and beyond. SpaceX's Starship, for instance, aims to carry up to 100 passengers to Mars, while Blue Origin's New Glenn rocket is designed to make space tourism and industrialization more accessible. The ISS, a collaboration between NASA, Roscosmos, ESA, JAXA and CSA, is a testament to the power of international cooperation. Orbiting Earth at an altitude of about 400 kilometers, the station serves as a laboratory for scientific research and a testing ground for technologies needed for long-duration space travel. Since its first component was launched in 1998, the ISS has hosted over 260 astronauts and cosmonauts from 21 countries. conducting research in microgravity that has advanced fields such as biology, physics, and materials science. Lessons learned on the ISS will be critical for future missions to the Moon, Mars, and other destinations in the solar system. For example, NASA's twin study, which compared the health of astronaut Scott Kelly after a year in space to his twin brother Mark on Earth, has provided insights into the effects of long-term space travel on the human body. Speculation. Could humanity one day become a multiplanetary species? Elon Musk's vision of colonizing Mars hinges on the development of reusable rockets and in situ resource utilization, using local materials to support human habitation. If successful, Mars could become a second home for humanity, a stepping stone to even more distant frontiers. However, the challenges are immense. Mars has a thin atmosphere composed mostly of carbon dioxide, average temperatures of 80 galaxies, 62 degrees, and radiation levels far higher than Earth's. To survive, colonists would need to extract water from Martian soil, grow food in hydroponic systems, and build habitats shielded from cosmic rays. Despite these hurdles, the possibility of a self-sustaining colony on Mars by the mid-21st century is not out of reach. Speculation. Life in space will require not just technological innovation, but also a shift in how we think about humanity's place in the universe. The concept of Earth independence, the ability to live and thrive without relying on resources from our home planet, is a central goal for many space advocates. This idea extends beyond Mars to the asteroid belt, where minerals and water ice could be harvested to support deep space missions, and even to the moons of Jupiter and Saturn, where subsurface oceans might harbour conditions suitable for life. Such ambitions are not without controversy. Critics argue that the resources spent on space exploration could be better used to address pressing issues on Earth, such as climate change and poverty. Yet proponents counter that the pursuit of space not only inspires technological progress, but also fosters a global perspective that could help unite humanity. Known, the ISS is a hub for scientific research and international collaboration in space. It has enabled breakthroughs in medicine, engineering, and our understanding of the cosmos. The station's success has shown that sustained human presence in space is possible, even in the harsh conditions of low Earth orbit. Unknown. The viability of long-term human habitation on Mars and other celestial bodies remains an open question. While robotic missions like NASA's Perseverance rover have provided valuable data about Martian soil and atmosphere, the physiological and psychological challenges of living on another planet are still largely untested. Additionally, the ethical and legal frameworks governing space colonization are still in their infancy, raising questions about ownership, resource extraction, and the rights of potential off-Earth communities. To be continued. Part 15. The Moon's Allure. What if the key to our future is hidden on the Moon? The glowing orb that has inspired poets, scientists, and dreamers for millennia may hold the practical solutions to humanity's most pressing challenges in space exploration. Observation. The Moon, our closest celestial neighbour, has long captivated human imagination. From the Apollo missions of the 1960s and 1970s to the upcoming Artemis program, the Moon has been a focal point of space exploration. Its proximity to Earth, just 3 days' travel away, makes it an ideal testing ground for technologies needed for deeper space missions. The Apollo program alone brought back 842 pounds of lunar rocks and soil, which have revolutionized our understanding of the solar system. These samples revealed that the Moon is approximately 4.5 billion years old, nearly as ancient as Earth itself. The lunar surface is pockmarked with over 300,000 craters, each one a time capsule of the early solar system's chaotic history. The Moon's allure extends beyond its scientific value. Its gravitational pull stabilizes Earth's axial tilt, creating the stable climate that has allowed life to flourish on our planet. Without the Moon, Earth might have experienced wild swings in temperature, making it difficult for complex life to evolve. The Moon also blocks a significant amount of space debris from striking Earth, acting as a cosmic shield. Its presence in the night sky has guided explorers, inspired mythology, and sparked countless stories across cultures. Interpretation. The Moon is more than just a barren rock. It is a treasure trove of resources, including helium-3, a rare isotope that could one day fuel fusion reactors, and water ice, which could be processed into rocket fuel. Helium-3, virtually non-existent on Earth, is abundant on the Moon due to solar wind bombardment over billions of years. Estimates suggest that as little as 25 tons of helium-3 could power the entire United States for a year, making it a potential game-changer for energy production. Water ice, discovered in permanently shadowed craters near the lunar poles, could be electrolyzed into hydrogen and oxygen, providing fuel for rockets and breathable air for astronauts. This would dramatically reduce the need to launch supplies from Earth, lowering the cost of space missions. The lunar surface also preserves a record of the early solar system, with craters and rocks dating back billions of years. Studying these features could shed light on the origins of the Earth-Moon system and the formation of planets. For example, the Moon's far side, shielded from Earth's radio interference, is an ideal location for radio telescopes that could peer into the universe's earliest moments. The lunar soil, or regolith, contains minerals and metals like titanium, iron and aluminum, which could be used to construct habitats and infrastructure on the Moon. Speculation. Could the Moon become a stepping stone to the stars? Some envision a future where lunar bases serve as way stations for missions to Mars and beyond. By mining the Moon's resources and using them to support human habitation, we could reduce the cost and complexity of deep space travel, making it more accessible and sustainable. NASA's Artemis program, slated to return humans to the Moon by 2025, aims to establish a sustainable lunar presence by the end of the decade. Private companies like SpaceX and Blue Origin are also developing technologies to support long-term lunar habitation, including reusable rockets and lunar landers. The Moon's low gravity, about 1/6 of Earth's, makes it an ideal environment for testing technologies for other low-gravity worlds such as asteroids and Mars. Researchers are exploring ways to use 3D printing with lunar regolith to build structures directly on the Moon, further reducing the need for Earth-based supplies. Additionally, the Moon's lack of atmosphere makes it an ideal location for astronomical observatories free from the distortions caused by Earth's air. Known. The Moon is rich in resources including helium-3 and water ice, and preserves a record of the early solar system. Its proximity to Earth makes it a practical and cost-effective destination for testing technologies needed for deeper space missions. Unknown. The feasibility of large-scale lunar habitation and resource utilization remains an area of ongoing research. Challenges include the Moon's extreme temperature swings, which range from 280 Tastaf in shadowed craters to 260 in sunlight, and the long-term effects of lunar dust on equipment and human health. To be continued, Part 16, The Red Planet's Promise. Could Mars hold the key to humanity's future? This question fuels some of the most ambitious scientific and engineering projects of the 21st century. Mars, with its rust-red landscape and thin, cold atmosphere, is both a challenge and an opportunity, a harsh world that might become a second home for human civilization. The planet's stark beauty, from the towering heights of Olympus Mons to the sprawling depths of Valle Marineris, inspires awe and ambition. Its skies, painted in hues of pink and orange by suspended dust, offer a glimpse into a world that is both alien and eerily familiar. Observation. Mars, the fourth planet from the Sun, has captivated us for centuries. Known as the Red Planet due to its iron oxide-rich surface, Mars boasts striking features. Olympus Mons, the solar system's largest volcano, stretches over 600 kilometers wide and soars 21.9 kilometers high, dwarfing Earth's Mount Everest. Valles Marineris, a vast canyon system, spans 4,000 kilometers, long enough to stretch across Europe. Ancient riverbeds such as the 1,000-kilometer-long Nergal Vallis and polar ice caps suggest a wetter past, offering potential resources for future human explorers. These ice caps could provide enough water to cover Mars in a 35-meter-deep layer, if melted. In 2018, the Mars Express orbiter detected a stable body of liquid water beneath the southern polar ice cap, hinting at Mars's potential habitability. These subsurface lakes, hidden under layers of ice and dust, may harbour microbial life or provide water for future settlements. Additionally, Martian soil contains perchlorates, which could be used to extract oxygen for future missions, a process demonstrated by the MOXIE experiment aboard Perseverance. This small, gold-plated device has successfully produced breathable oxygen from the Martian atmosphere, a critical step towards sustainable human presence. Interpretation. Mars is the most Earth-like planet, with a day just 40 minutes longer than ours and similar seasons due to its axial tilt. Its thin carbon dioxide-rich atmosphere is inhospitable, with temperatures plunging to 195 degrees Fahrenheit, 126 degrees Celsius at the poles, and rising to a high of 70 degrees Fahrenheit, 20 degrees Celsius, at noon near the equator. Despite these extremes, the presence of water ice and other resources makes it a prime target for colonization. Rovers like Curiosity and Perseverance are exploring Mars, searching for signs of past life. Curiosity, in Gale Crater since 2012, has detected organic compounds and methane fluctuations, while Perseverance, in Jezero Crater since 2021, is collecting soil and rock samples for future return to Earth. The Mars 2020 Perseverance rover also carries Ingenuity, a helicopter that made history in April 2021 by performing the first powered flight on another planet, opening possibilities for aerial exploration. Orbiters like MRO and Mars Odyssey continue to map Mars's surface, aiding in the identification of resources and landing sites. These missions have revealed Mars to be a dynamic world, with dust storms that can engulf the entire planet and seasonal changes that reshape its polar caps. Speculation: could Mars become humanity's second home? SpaceX's Starship aims to carry humans and cargo to Mars, potentially starting crewed missions in the 2030s. However, the journey poses challenges: prolonged weightlessness, radiation, psychological stress, extreme temperatures, and dust storms. Despite these obstacles, Mars's proximity to Earth and its similar day-night cycle make it a realistic target. NASA's Artemis program, aiming to return humans to the Moon by 2025, is a stepping stone to Mars, testing technologies like in-situ resource utilization. For example, NASA's MOXIE experiment and other developments in 3D printing with Martian regolith could allow future settlers to build habitats and infrastructure using local materials. Mars's gravity, about 38% of Earth's, could prevent long-term health issues associated with microgravity, while making spacecraft launches from the surface more feasible. Its moons, Phobos and Deimos, could serve as staging areas for future missions, with Phobos's low gravity making it an ideal site for constructing and launching interplanetary spacecraft. However, the viability of long-term human settlement and the potential discovery of life on Mars remain uncertain. The effects of prolonged human exposure to Mars's conditions are untested, and ethical questions about resource management and societal structures on Mars are complex and unresolved. For instance, the discovery of life on Mars, whether extinct or extant, would raise profound questions about planetary protection and the ethical implications of human colonization. These challenges and unknowns will shape the future of human exploration and habitation on the Red Planet. To be continued. Part 17. The Giant's Secrets. What if the largest planets hold the smallest clues to life? The gas giants Jupiter and Saturn dominate the outer solar system with their sheer size and astonishing features. Jupiter, the king of planets, is more than twice as massive as all the other planets combined, its swirling atmosphere a canvas of vibrant clouds and storms. The Great Red Spot, a hurricane-like storm that has been active for at least 350 years, is one of the most iconic features in the solar system, large enough to swallow Earth whole. Saturn, the ringed planet, is equally mesmerizing. Its rings, visible even through small telescopes, stretch out over 280,000 kilometers from the planet, yet are incredibly thin, averaging only about 10 meters in thickness. These rings are not solid, but composed of countless particles of ice and dust, each orbiting Saturn like a tiny moon. Both giants are more than just spectacles. They are gatekeepers to some of the most intriguing worlds in our solar system, their moons. Observation. Jupiter and Saturn, the gas giants of our solar system, are worlds of extremes. Jupiter's atmosphere is a churning cauldron of hydrogen and helium, with wind speeds that can exceed 400 kilometers per hour. Its magnetic field is the strongest of any planet, trapping charged particles that create intense radiation belts. Saturn, while also a gas giant, is less dense than water. It would float if placed in a large enough body of water. Its rings, though stunning, are not its only claim to fame. Saturn's moon Titan is the only moon in the solar system with a substantial atmosphere, thicker than Earth's and rich in organic compounds. Both giants are orbited by moons that hint at the potential for life, turning these distant worlds into beacons of scientific curiosity. Jupiter's moon Europa, slightly smaller than Earth's moon, is covered in a thick layer of ice, beneath which lies a global ocean of liquid water. This ocean, estimated to be up to 100 kilometers deep, is kept warm by tidal forces exerted by Jupiter's immense gravity. These same tidal forces flex Europa's icy crust, creating cracks and fissures that allow water to interact with the moon's rocky interior. This interaction could provide the necessary ingredients for life, such as minerals and chemical nutrients. Saturn's moon Enceladus, though much smaller, is no less intriguing. With a diameter of only 500 kilometers, it is one of the brightest objects in the solar system, reflecting nearly all the sunlight that hits its icy surface. Its geysers, located near the South Pole, spew plumes of water vapor and ice particles into space, feeding Saturn's tenuous E-ring. These geysers are evidence of a subsurface ocean, heated by tidal interactions with Saturn, and possibly by radioactive decay in the moon's core. Interpretation: Europa and Enceladus are not just frozen worlds. They are dynamic environments where the conditions for life may exist. Europa's ocean is thought to contain more water than all of Earth's oceans combined, and its icy shell acts as a protective barrier against Jupiter's harsh radiation. The moon's surface is marked by chaotic terrains, regions where the ice has been disrupted and reformed, suggesting ongoing geological activity. Enceladus, meanwhile, is a world of cryovolcanism, where water and other materials are forced to the surface through cracks in the ice. The Cassini spacecraft, which flew through Enceladus's plumes, detected complex organic molecules, including methane and propane, as well as traces of silica, a mineral that on Earth is often associated with hydrothermal vents. These vents, found deep in Earth's oceans, support ecosystems teeming with life, even in the absence of sunlight. Both moons are prime targets for future missions aimed at detecting signs of extraterrestrial life, offering scientists a rare opportunity to explore worlds that may resemble early Earth. Speculation: could the gas giants and their moons be the key to understanding the origins of life? Some theories suggest that life may have emerged not on Earth but on worlds like Europa or Enceladus, carried to our planet by comets or asteroids, a process known as panspermia. If life exists elsewhere in the solar system, it could shed light on the universal principles governing the emergence of complexity and consciousness. For example, if life on Europa evolved independently of life on Earth, it would suggest that life is a common outcome of the right chemical and environmental conditions. Conversely, if life is absent despite the presence of water and organic compounds, it could imply that life is far rarer than we hope. The search for life beyond Earth is not just about discovering alien organisms. It is about understanding the fundamental rules of biology and whether they apply across the cosmos. Known: Europa and Enceladus harbour subsurface oceans that could potentially support life. Europa's ocean is kept liquid by tidal heating, while Enceladus's geysers provide direct evidence of an active water cycle. Both moons exhibit signs of geological activity, suggesting the presence of energy sources that could drive biological processes. Unknown: the presence of life on these moons and the mechanisms by which it could have emerged remain open questions. Future missions, such as NASA's Europa Clipper and the European Space Agency's JUICE, aim to study these moons in unprecedented detail, searching for signs of habitability and, perhaps, the first evidence of life beyond Earth. To be continued. Part 18. The Ice Giant's Enigma. What if the coldest planets hold the hottest secrets? The ice giants Uranus and Neptune are not merely distant orbs but dynamic worlds shrouded in enigma. Uranus, with its astonishing axial tilt of 98 degrees, presents a spectacle unlike any other planet. Its sideways rotation subjects it to extreme seasons where each pole faces the sun for 42 Earth years at a time, plunging the other half of the planet into an equally long, frigid winter. This bizarre orientation may have been the result of a cataclysmic collision with an Earth-sized object billions of years ago, a theory supported by the planet's unusually low internal heat compared to other gas giants. Neptune, on the other hand, is a deep azure sphere, its striking blue color a result of methane gas absorbing red light in its atmosphere. Its winds are unparalleled in the solar system, reaching speeds of up to 2,000 kilometers per hour, driven by forces scientists are still working to understand. Observation: Uranus and Neptune, the ice giants of our solar system, are worlds of mystery. Uranus's atmosphere is a frigid 216 degrees, making it the coldest planet in the solar system, despite being closer to the Sun than Neptune. Its pale cyan hue is due to the presence of methane, which absorbs red light and scatters blue. Meanwhile, Neptune's storms are legendary. The Great Dark Spot, a storm larger than Earth, was first observed by Voyager 2 in 1989, though it has since dissipated, leaving scientists to ponder the life cycle of such monumental weather patterns. Both planets are orbited by moons that hint at the potential for unique geological and atmospheric processes, far beyond what was initially imagined. Interpretation: Uranus's moon, Miranda, is a world of stark contrasts, with towering cliffs up to 5 kilometers high and deep canyons that suggest a complex geological history. Its surface is a patchwork of strange terrains, including grooved plains and chaotic regions that may have been reshaped by violent tectonic activity or even the reassembly of fragments from a past catastrophic impact. Neptune's moon, Triton, with its geysers of nitrogen gas erupting up to 8 kilometers into space, hints at the presence of a subsurface ocean and an active internal heat source. Triton's retrograde orbit, moving in the opposite direction to Neptune's rotation, suggests it was likely captured from the Kuiper Belt, a distant region of icy bodies beyond Neptune. Both moons are targets for future missions aimed at unraveling the mysteries of the ice giants and their potential for harboring life. Speculation: could the ice giants and their moons be the key to understanding the outer reaches of the solar system? Some theories suggest that Uranus and Neptune may have migrated from closer to the Sun, their orbits disrupted by gravitational interactions with the gas giants Jupiter and Saturn. This migration could explain their peculiar compositions and the presence of their unique moons. Studying these worlds and their moons could shed light on the dynamics of planetary formation and the potential for life in the coldest corners of the cosmos. The upcoming missions, such as NASA's proposed Uranus orbiter and probe, aim to dive deeper into these enigmas, exploring the ice giants' magnetospheres, atmospheres, and moons with unprecedented detail. The ice giants challenge our understanding of planetary evolution. Their interiors are believed to be a slushy mix of water, ammonia, and methane ices surrounding rocky cores, unlike the hydrogen-helium dominance of Jupiter and Saturn. This composition makes them a bridge between the gas giants and the terrestrial planets, offering insights into the diversity of planetary structures in our solar system and beyond. Additionally, the study of their rings, Uranus's narrow, dark rings and Neptune's fainter, more diffuse system, could reveal how such structures form and evolve, providing clues to the processes at work in other ringed planets. Known: Uranus and Neptune are orbited by moons with unique geological features and potential subsurface oceans. Their atmospheres are dynamic, with extreme weather patterns and chemical compositions that are still being deciphered. Unknown. The origins of these moons, the potential for life in the ice giant systems, and the exact mechanisms behind their internal heat and magnetism remain areas of active research. To be continued. Part 19. The Edge of the Solar System. What if the boundaries of our cosmic backyard are not as clear as we think? The edge of the solar system is not a stark line, but a gradual transition into the interstellar void. This vast frontier begins with the Kuiper Belt, a disc-shaped region beyond Neptune's orbit, stretching from 30 to 55 astronomical units, AU, from the Sun. Within this icy expanse lie hundreds of thousands of objects, remnants of the primordial solar system, frozen in time and space. Pluto, the most famous of these bodies, was demoted from planetary status in 2006, but its significance has only grown. Alongside Pluto are other dwarf planets like Eris, Haumea, and Makemake, each a world in its own right, with surfaces sculpted by cryovolcanism, impacts, and the faint glow of the distant sun. Observation. Beyond the orbit of Neptune lies the Kuiper Belt, a vast region of icy bodies and dwarf planets. Among these objects is Pluto, once considered the 9th planet but now reclassified as a dwarf planet. The Kuiper Belt is home to countless small worlds, including Eris, Haumea, and Makemake, each with its own unique characteristics and mysteries. Eris, for instance, is roughly the same size as Pluto but brighter, its surface coated in methane ice that reflects sunlight with an eerie brilliance. Haumea, shaped like a flattened egg due to its rapid rotation, is accompanied by 2 moons and a ring system, a miniature echo of the giant planets. The Kuiper Belt is not the only structure at the solar system's edge. Beyond it lies the scattered disk, a sparsely populated region where objects like Sedna and 2012 VP113 orbit in highly elongated paths. These bodies never come close enough to Neptune to be gravitationally influenced by it, suggesting that something else, perhaps a distant, undiscovered planet, may be shaping their orbits. Further out, the Oort cloud begins, a theoretical spherical shell of icy bodies stretching up to 200,000 AU from the Sun. This distant reservoir is the source of long-period comets, which plunge into the inner solar system on trajectories that take millions of years to complete. Interpretation. The Kuiper Belt is a remnant of the early solar system, a region where the building blocks of planets still linger. Studying these objects and their orbits can shed light on the formation and evolution of the solar system, as well as the potential for life in its outer reaches. The New Horizons mission, which flew past Pluto in 2015, revealed a world of unexpected complexity, with towering ice mountains and a thin atmosphere. Pluto's largest moon, Charon, also surprised scientists with its youthful appearance, suggesting recent geological activity despite its small size and distant location. The New Horizons mission did not end with Pluto. In 2019, the spacecraft performed a flyby of Arakoth, a small Kuiper Belt object shaped like a snowman. Arakoth's 2 lobes, connected by a narrow neck, are pristine relics of the early solar system, offering clues about how planetesimals, the seeds of planets, formed billions of years ago. Its reddish hue, likely caused by organic compounds processed by cosmic radiation, hints at the complex chemistry occurring even in the coldest corners of the solar system. Speculation. Could the Kuiper Belt be the key to understanding the origins of the solar system? Some theories suggest that the orbits of Kuiper Belt objects may be influenced by an undiscovered ninth planet, a massive world lurking in the outer reaches of the solar system. If such a planet exists, it could be a missing piece in the puzzle of planetary formation and the dynamics of the solar system. Known as Planet 9, this hypothetical world is predicted to be about 10 times the mass of Earth and to orbit at an average distance of 400 to 800 AU. Its gravitational influence could explain the clustering of orbits observed among certain Kuiper Belt objects. While Planet 9 remains purely speculative, its potential existence has sparked a renewed search for distant objects in the solar system. Astronomers are now scouring the skies using advanced telescopes like the Subaru telescope in Hawaii and the Vera C. Rubin Observatory in Chile to hunt for faint, slow-moving objects that might betray the presence of an unseen planet. If found, Planet 9 would not only rewrite textbooks, but also challenge our understanding of how planets form and evolve. Known, the Kuiper Belt is home to a diverse array of icy bodies and dwarf planets, including Pluto. These objects, along with the more distant scattered disk and Oort cloud, represent the outermost frontiers of the solar system. Missions like New Horizons have revolutionized our understanding of these regions, revealing worlds that are far more dynamic and complex than once imagined. Unknown, the presence of an undiscovered ninth planet and its potential influence on the orbits of Kuiper Belt objects remains speculative. The search for Planet 9 continues, driven by the desire to solve one of the greatest mysteries in modern astronomy. Meanwhile, the origins of the solar system's outer structures, from the Kuiper Belt to the Oort cloud, remain incomplete, awaiting further exploration and discovery. To be continued. Part 20. The Final Frontier. What if the universe is just the beginning? Observation. The universe is a vast and mysterious place, filled with wonders that challenge our understanding of reality. From the swirling arms of galaxies like the Milky Way, which stretches over 100,000 light-years, to the enigmatic depths of black holes, where time and space are warped beyond recognition, the cosmos beckons us with questions that have captivated humanity for millennia. What lies beyond the event horizon of a black hole, where not even light can escape? Are we alone in the universe, or do other civilizations exist among the estimated 100 billion stars in our galaxy alone? And how did it all begin? In the fiery furnace of the Big Bang, nearly 13.8 billion years ago. Every year, astronomers discover thousands of new exoplanets, worlds orbiting distant stars. As of now, over 5,000 exoplanets have been confirmed, each one a potential cradle for life. Yet, the questions persist. How many of these worlds harbour living organisms, and how might they compare to life on Earth? The Drake equation, a probabilistic argument used to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way, suggests that there could be tens of thousands of such civilizations, though the uncertainties are vast. The search for extraterrestrial intelligence, SETI, continues, scanning the skies for signals that might hint at the presence of other cosmic neighbors. Interpretation. The search for answers to these questions has led to remarkable discoveries. From the cosmic microwave background radiation, the echo of the Big Bang, discovered in 1964 by Arno Penzias and Robert Wilson, to the detection of gravitational waves in 2015. These ripples in the fabric of space-time, predicted by Einstein a century earlier, were first observed by the Laser Interferometer Gravitational Wave Observatory, LIGO, during the cataclysmic collision of two black holes over 1 billion light-years away. Yet, for every question we answer, new mysteries emerge, challenging us to push the boundaries of our knowledge and imagination. For instance, the nature of dark matter and dark energy, which together make up approximately 95% of the universe, remains one of the greatest enigmas in modern astrophysics. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, has been instrumental in probing the fundamental building blocks of the universe. In 2012, it confirmed the existence of the Higgs boson, the particle associated with the Higgs field that gives other particles their mass. However, the LHC has yet to detect any particles that could explain dark matter, leaving scientists to speculate about hypothetical particles like axions or WIMPs, weakly interacting massive particles. Meanwhile, the mystery of dark energy, the force thought to be accelerating the expansion of the universe, remains equally elusive. Observations from the Hubble Space Telescope and other instruments suggest that this cosmic acceleration began around 5 billion years ago, but its cause is still unknown. Speculation. Could the universe be just one of many, part of a larger multiverse where the laws of physics and the constants of nature vary from one realm to the next? Some theories, such as the many worlds interpretation of quantum mechanics, suggest that every possible outcome of every event spawns a new, separate universe. Others, like the brane theory and string theory, propose that our universe is just a three-dimensional brane floating in a higher dimensional space, with other branes, other universes existing nearby. If so, then the quest to understand the cosmos is not just a journey of discovery, but a voyage into the very heart of existence itself. One of the most intriguing ideas is the concept of the multiverse, where our universe is just one bubble in an infinite frothing sea of universes. In this scenario, each universe could have its own unique set of physical laws, constants, and even dimensions. Some physicists, like Max Tegmark of MIT, have proposed that there could be 4 distinct levels of multiverses, ranging from distant Hubble volumes beyond our observable universe to entirely mathematical structures that encompass all possible realities. While these ideas remain purely speculative, they challenge us to think beyond the boundaries of our own cosmic horizon. Known. The universe is a vast and complex place, filled with mysteries that challenge our understanding of reality. We have mapped the cosmic microwave background with unprecedented precision, revealing fluctuations in temperature that correspond to the seeds of galaxies and stars. We have detected gravitational waves, confirming one of Einstein's most daring predictions. We have even imaged the shadow of a black hole for the first time, thanks to the Event Horizon Telescope's groundbreaking observations of M87 TACs in 2019. Unknown. The nature of the multiverse and the potential for other universes with different laws of physics remain purely speculative. We do not yet understand the fundamental nature of dark matter or dark energy, despite their dominance in the cosmic landscape. The search for extraterrestrial life continues, but we have yet to find definitive evidence of even the simplest microbial organisms beyond Earth. And perhaps most profoundly, we still do not know whether we are alone in the universe or part of a cosmic community of intelligent beings. Finale, final countdown. As we stand on the precipice of a new era of space exploration, the mysteries of the universe beckon us with ever greater urgency. From the search for extraterrestrial life to the quest to unravel the secrets of black holes and dark matter, the cosmos challenges us to push the boundaries of our knowledge and imagination. The Mars 2020 Perseverance rover is currently collecting samples from the Red Planet, searching for signs of ancient microbial life, while the Europa Clipper mission, set to launch in the coming years, will investigate Jupiter's icy moon Europa for evidence of a subsurface ocean that could harbour life. In the coming decades, new technologies and discoveries will open up unprecedented opportunities to explore the farthest reaches of the cosmos. The James Webb Space Telescope, launched in 2021, will peer into the atmospheres of exoplanets in search of biosignatures like oxygen, methane, or other chemical markers of life. Its infrared capabilities will allow it to see farther back in time than ever before, potentially revealing the first galaxies that formed just a few 100 million years after the Big Bang. Meanwhile, the next generation of gravitational wave detectors, such as the Einstein Telescope and the Cosmic Explorer, will listen for the faint whispers of the universe's most cataclysmic events, from colliding neutron stars to the mergers of supermassive black holes. Yet even as we venture farther into the unknown, the ultimate mystery remains. Why do we strive to understand the universe? Is it simply a quest for knowledge, or is it something deeper, a longing to connect with the cosmos and find our place within it? The Voyager 1 spacecraft, launched in 1977, is now the most distant human-made object in space, travelling through the interstellar medium more than 15 billion miles from Earth. On board is the Golden Record, a collection of sounds, images and music from our planet, intended as a message in a bottle for any extraterrestrial civilizations that might one day encounter it. This gesture, though symbolic, speaks to our enduring desire to reach out to the cosmos and share our story. Perhaps the answer lies not in the stars, but in the human heart. For as long as we have gazed up at the night sky, we have been driven by a profound desire to know, to understand the mysteries of existence, and to find meaning in the vast, silent expanse of the cosmos. The ancient Greeks saw the heavens as the realm of the gods, while medieval astronomers like Copernicus and Galileo risked their lives to challenge the prevailing view of an Earth-centered universe. Today, scientists and dreamers alike continue this tradition, pushing the frontiers of our understanding with every new discovery. And so, as we embark on this journey through the mysteries of space, let us remember that we are not just observers, but participants in the grand story of the universe. Each discovery, each new insight, brings us one step closer to understanding not just the cosmos, but ourselves, and the eternal questions that bind us to the stars. The Apollo 8 mission in 1968 gave us the iconic Earthrise image, a reminder of our planet's fragility and beauty against the backdrop of the cosmos. It was a moment that forever changed our perspective, underscoring the interconnectedness of all life on Earth and our shared destiny as explorers of the universe. For in the end, the greatest mystery of all may be the one that lies within us, the human spirit, forever reaching for the infinite, forever striving to touch the face of the universe and to know its secrets. And perhaps, in that quest, we will find not just answers, but a deeper connection to the cosmos, and to the eternal mystery that is the heart of all existence. As Carl Sagan once said, somewhere, something incredible is waiting to be known. It is this insatiable curiosity, this unquenchable thirst for knowledge, that defines us as a species and propels us ever forward into the unknown. Fade to black.